This is going to be a short lecture on line integrals. Recall that when f of x is a positive function, the integral written here represents the area underneath the graph of y equals f of x and above the x-axis between x equals 0 and x equals a. A line integral is a generalization of this idea. Instead of the x-axis, we're going to have a curve in the xy plane, and it's the area above that curve and below some surface, z equals f of xy. So this is the picture. We have some curve in the xy plane, and the height is given by z equals f of xy, whatever f of xy is above the point xy in the xy plane. So the curve we put here on this integral symbol, and this is the height, f of xy, and ds is telling you that it's a piece of the arc length. That's the notation we had before for arc length. And what you can think of is if you draw a little delta s here along this arc here, the height's going to be this function again. So the area of that rectangle would be f times delta s. And when you let delta s get small and number of pieces get large, you're getting f for the height and ds for that thickness. What happens to that is delta s gets small. So here is another picture of sort of the type of area we're trying to find. But the main point of this slide is to remind you that if we have a curve C, that in general means that you can replace the variables in your problem with a function of one variable, the parameter. So we can think of x and y as being a function, say, of t or some other variable. And we want to calculate the value of this by doing exactly that, rewriting this in terms of that variable. So this is saying what I was mentioning before, where this is the height of your rectangle, this is the thickness, and you're summing over those to get the area that we want. But we want to let the delta s get small and the number of pieces get large to better and better approximate that area. And in the end, that is what this is representing, this line integral. We can have the same thing with three variables, defined the same way, except for an extra variable there. And the meaning might be a bit different here. One way to think of this is maybe you have a wire that's in the shape of some curve. And if you think of that wire as describing the curve here, then if this is the density at a point on that wire, this would be the mass of that wire. So this line integral, the value of that would be the mass of the wire. So this does have a nice interpretation when we throw in an extra variable z and this curve is in space. So how do we want to approach this again? Well, we want some curve defined in terms of a parameter t or some other variable. So if I have x equals x of t and y equals y of t, and possibly z equals z of t to describe this curve. T is going to be in some range, a, b, telling you where you are in that curve, the limits of t. And we want ds to be what it was before for part of the arc length here. It's the square root of x prime squared plus y prime squared. And if there's a z, you would add in a plus z prime squared. So this is what represents a part of the arc length that we used before for finding arc length. So we can rewrite this integral then just by simply replacing x and y with what they're equal to in terms of their parametric equations. So x of t and y of t, and the ds in terms of what it's equal to in terms of t. Then we just have an integral in terms of t, where t is going from a to b. And that's how we would calculate this. Once we put everything in terms of t, we just do the integral. So this is what we were just talking about. Recall that if r of t is the vector x of t, y of t, r prime of t, the length of that will be the same thing as this. We can do the same thing with three variables. That just gives you an extra z prime of t squared here underneath the radical that we want to use. And of course, z gets replaced with z of t, whatever z of t happens to be. So let me go ahead and do an example. So here we have x just being t, y being t squared, and z is 2/3 t cubed. T is between 0 and 1. So this is telling me what my curve is. How I want to solve this again is I want to replace x and y with what they're equal to, t and t squared. And then ds, what it's equal to in terms of t. Let's do ds first, since it's a little bit more complicated. We're going to take the derivatives of each of these and then square them. And in the end, we want to take the square root of that. So let's check what this equals. X prime is just 1, so we get 1 squared. Y prime will be 2t, so I have 2t squared. Here, when I take the derivative of z, the 3's will cancel. I get 3t squared. That'll cancel with that 3. I'll just have 2t squared, and then we want to square that. So rewriting that, we have 1 plus 4t squared plus 4t to the 4th when I square the 2t squared. We want to make sure this looks like something nice. We want it to be something squared because we want to take the square root of it. So this is something squared. It's 1 plus 2t squared squared. So we can see that. And then what we want to do is take the square root of this for ds. So we're going to have 1 plus 2t squared when we take the square root here. So ds is going to be 1 plus 2t squared dt. So when I set up this line integral, I'm going to have t going from 0 to 1. T is going from 0 to 1. And ds is going to be the 1 plus 2t squared dt, the square root of this. The t cubed is coming from x times y. X is t and y is t squared. So x times y will be t cubed. So I've just replaced everything in this integral, this line integral, and put them in terms of t. So xy is t cubed, ds is 1 plus 2t squared dt. So I want to integrate now t cubed plus 2t to the 5th. That's going to give me t to the 4th over 4 plus 2t to the 6th over 6. And I want to evaluate this from t equals 0 to 1. At 0, we get 0. At 1, we're going to get 1/4 plus, and this is just 1/3. So that's going to give me 7/12. So the value of this line integral is 7/12. There is another way you'll see line integrals written, and that is in this form. And this is basically breaking it up into an x component and y component. And we want to know how to evaluate a line integral that looks like this. Now, really, you're going to do exactly what you would think you would do. Now, you might think to yourself, I have no idea what to do, but if I actually write down a problem, you probably would guess right here. So here's the line integral we want to evaluate. I even have an extra dz in here that we didn't have up here. And c is this curve now in space, where t is going from 0 to 1. This is the same curve we had before. So how would you evaluate this? Well, a little bit of thought. You want to go ahead and replace y with t squared, x with t, so this would be t squared, and then the minus 3xyz, well, you got to multiply these out, multiply by minus 3. And what about the dx, the dy, and dz? Yes, dx is dt, dy will be 2t dt, and we calculate dz here also, which will be 2t squared dt. So again, first we're going to calculate dx, dy, and dz. Dx is dt from here. Dy is 2t dt. Here when I take the derivative, I have a 3t squared. The 3 will cancel. So I have just 2t squared dt. So dz is 2t squared dt. Now we have x, y, z, dx, dy, and dz all in terms of t. So we just put them up here. T is going from 0 to 1 again. The y is t squared. Dx is dt, so I have y times dx. dt. Then I have x squared here. X was t, so that's giving me the t squared. dy was 2t dt. Then I have minus 3 times x, y, z. X is t, y is t squared, z is 2/3 t cubed. So that's the minus 3xyz. And then dz is 2t squared dt. So I have everything written out here then. I want to simplify that. I have t squared, 2t cubed. We have a 3 times 2/3, that's 2. So we're going to get 4 with a minus sign. T times t squared times t cubed is t to the 6th, times another t squared is t to the 8th. So this will be minus 4t to the 8th. So t squared again, 2t cubed, and a minus 4t to the 8th for this part. So we want to integrate that. We're going to get t cubed over 3 plus 2 times t to the 4th over 4 minus 4 times t to the 9th over 9. We want to evaluate this from t equals 0 to 1. At 0, again, it's 0. At 1, we'll have 1/3 plus 1/2 for that, minus 4/9. 1/3 is 3/9. 3/9 minus 4/9 is minus 1/9. So we have 1/2 minus 1/9, and that's going to be 7/18. So 7/18 is the value of this line integral. Let's do another example. This one's from a book. We want to integrate sine x dx plus cosine y dy, where c is the top part of a circle of radius 1 centered at the origin. We're going from 1, 0 on that circle to minus 1, 0. And then we're going from minus 1, 0 to minus 2, 3. So in terms of a picture, well, you're starting at 1, 0, you're going to minus 1, 0, the top half of the circle. And then you're going from minus 1, 0 to minus 2, 3. So there are two pieces to this, the half circle and the line segment. And the way you should evaluate this is to break it up into those two pieces, describe each separately with some parametric equation that's not given here, so we have to write down those parametric equations. This first one is a half circle starting at 1, 0 and going to minus 1, 0. The circle of radius 1 centered at the origin. And you should be accustomed to what that looks like in parametric form because it's just really the same thing as the unit circle you learned when you're learning your trig values. So x equals cosine of t, y equals sine t is giving me the values of x, y along the unit circle. And if we start at 0, we're at 1, 0. And if we go to pi, we're going to be at minus 1, 0. So this is giving me the first half of that circle of radius 1 centered at the origin. For the line segment, we want a line segment going from minus 1, 0 to minus 2, 3. You should remember that we learned that at the beginning of the semester, how to write that in terms of parametric equations. We write down the equation of the line going through these two by using this point, minus 1, 0. So x equals minus 1 plus something times t, and y equals 0 plus something times t. And you figure out the times t part by using the vector going from this point to this point. So that vector is going to be minus 2 minus a negative 1, which gives me minus 1. And then it's going to be 3 minus 0, which gives me 3. So this is a vector in the xy plane. Its coordinates are minus 1 and 3. Those will be the coefficients of t. So the coefficients of t again are minus 1 and 3. The point I want to use is minus 1, 0. So there's an implied 0 here. We have minus 1 and 0 for the point. And as long as I start with the initial point of my line segment and use the vector going from that to the other point, then I can take t between 0 and 1. And that's going to give me the line segment I want. So that's what we did earlier in the semester. So we have the parametric equations for a half circle and the parametric equations for a line segment. So to set up this integral, we want to break this up into an integral that describes this part plus another integral that describes this part. So I'm going to write this down. We'll go through this. T is going from 0 to pi for the half circle. And where did I get this part from? I'm just looking at what I have up here. I want sine x, sine of cosine of t, because x is cosine of t. And then I want dx. Well, dx will be minus sine t dt. So this is sine of x dx. For the second part, I want cosine of y, cosine of sine t, cosine of sine t, cosine of y, and dy will be cosine t dt. Okay? So that describes where this came from. It's just using this and plugging what x is and dx and dy. I want to do the same thing with that line segment. For that line segment, t is between 0 and 1. I want sine of x again, dx, sine of this, sine of minus 1 minus t, and dx now will be minus dt, minus 1 dt. Then I want plus cosine of y dy, cosine of y will be cosine of 3t, and dy will be 3 dt. So this is agreeing then with what we had up here. So this would be the value of this line integral. Now, I'm not going to evaluate this, but it's actually not as bad as it might look. For example, all you do would write this as 4 integrals, integrate this dt, and then this dt, with t going from 0 to pi, and then integrate this dt and this dt with t going from 0 to 1. When I integrate this part, that might look a little messy, just do a u substitution, u equals cosine of t, and we have sine u du here. And for this, do the same thing. If I take u to be sine t, this will be cosine u du. So you can evaluate this. It's not too bad, but I'm not going to do that here. That's how you would set this up as a line integral